MIT Energy Initiative, or MITEI as we dub it, has been going now for about 13 years. And we were built, as Kevin described, around a very strong engagement model, engaging with industry. And the engagement with ExxonMobil that Vijay just described around this kind of problem is, I think, typical of why and how we do that, because the back and forth between our expertise and our talent base with the knowledge base and experts at industry like ExxonMobil, I think makes us both better at how we go about these problems, and I think has led to some pretty unique characteristics to the SESAME tool that you're going to hear about. It's also nice to talk to OGCI because, amongst other things, I think all of the inaugural members of OGCI were members of MITEI, and today we still work with a pretty broad swath of members of OGCI as you've grown in size over the years. So I think that in this spirit of academic industry cooperation and collaboration, I think SESAME offers us a really interesting opportunity for a win-win. What we're trying to do with SESAME, as Vijay described, is very much, and I think very well aligned with OGCI's target outcomes. So the needs to quantify greenhouse gas emission reductions, and also to understand quantitatively the opportunities for recycling CO2 or storing CO2. It also, I think, can, as you'll see, be a very interesting support tool for individual company targets. And I hope that comes out in the presentation, and you take advantage of the discussion to ask specific questions you might want to delve into. Vijay also touched on what I regard as the really unique design feature of SESAME. I think what really sets us apart from other tools that you could access to look at life cycle analysis. And I'm sure all of you have some life cycle analysis within your own companies. But this modular feature, which we will come back to over and over again during this presentation, allows quite a few very important things for you as customers. One is it allows companies to leverage their own internal LCA analyses. You've worked on analyses, as I said. You have your own models. You have your own data sets that can be useful in understanding your own systems. Rather than replacing that with something else entirely, what SESAME allows you to do is connect what you've done with other models, other analyses, other large data sets to better understand how you play in the energy system as a whole and the economy as a whole. Now, the modular design allows, at its heart, customization to be done quite easily. The modules and databases we have are open source. They can be swapped out for company-specific analyses, models that you might have with data sets that you have, or proprietary data sets that you're used to using in your own work. So you don't, again, have to walk away from that, but you can do your own analyses in a non-publishable form. The work we do at MIT, of course, is publishable, but the tool is quite adaptable to however you want to use it in your own company planning and strategy. It also allows us to assemble very quickly LCA analyses that we don't have in the system, because you can put these modules together in different ways, as we'll discuss, but both in the overall design and with many examples in the presentation, to understand new opportunities for meeting energy demand in the face of increasing constraints on GHG emissions. It lets us understand quantitatively the implications in both directions of changes in one part of the energy sector on changes in another. Again, hark back to something that Vijay said. So for example, as we see changes in the transportation system, how does that impact other parts of the energy space? For example, the energy power generation part of the energy sector, and vice versa. How does what has happened in the power sector affect transportation, energy use in buildings, energy use in the industrial sector? It also, I think, very importantly, allows us to apply LCA methods rapidly to different regions of the world. So as we go forward, there's both huge opportunity and huge challenge in how we help the developing world decarbonize. And those systems are obviously different and have different resources than in the developed countries or in regions like the EU or in the US. And so how do we understand those systems easily without starting from scratch and designing new systems? And lastly, again, as Vijay said, I think having a common tool, sort of a language that we can use in different companies, in different government agencies, to quantify our understanding of pathways and their implications for greenhouse gas emissions reductions, I think helps to make the conversations much more productive. So we're not arguing about how did you do that and why did you make that assumption, and so on. We have a common language to talk from. I'd like to show one slide. It'll be the worst slide you'll see today. And I have it to show you the modular structure of SESAME. You are not supposed to be able to read everything on this slide. In fact, we often joke and call this the eye chart. I'm not sure what your vision is if you can read everything on this chart, but it's meant to illustrate this idea that we're broken up in this modular structure that creates a high degree of flexibility and adaptability going forward. So the design is based on breaking down the life cycle analysis into the 6 columns in this chart, or vectors that begin on the far left side with the upstream, we call it, or I think of it as energy source harvesting. So how do we harvest an energy source like natural gas? So how do we do exploration and production for that gas? And there are different modules for different kinds of natural gas, whether it's conventional or shale or whatever. You can harvest biomass, literally. You can harvest solar energy using photovoltaics or concentrated solar power. So a whole range of different energy resources that you could harvest, and then understand through modules in that column, what's the life cycle, what's the carbon emissions, greenhouse gas emissions component to that. Those harvested resources need to be moved by pipeline or truck or rail or ship to a process that converts those to products that are useful for different parts of the economy. So that could be production of fuels for vehicles, gasoline, diesel, for example, could be electricity. So you have power plants of various designs, nuclear, combined cycle, natural gas plants, and so on. In some cases, you will want to capture the CO2 from that. And we think CCUS is such an important part of the energy system going forward. We have a separate column for that, looking at different methods for capturing CO2, CO2 compression, different utilization pathways for CO2, different pathways for storage of CO2. So you can or cannot, depending on how you're designing your system, add in a CCUS piece. And again, that's highly adaptable. And then finally, the last two columns look at how do we move that to the end user, and what's the emissions impact of that part of the process. And finally, the end use application and emissions associated with that. And of course, the emissions occur across this whole chain, and how much of the emissions occurs at each part depends on the particular pathway you're constructing. This modular structure allows us to construct more than 1,000 pathways with the modules we have now by picking a piece from each one of these columns, with the possible exception of the CCUS piece, and then summing the life cycle emissions from each of those segments. You can also then couple together multiple of these pathways to build up an energy system. For example, we've illustrated this on the state of California's energy system, and use that to help understand how generation from solar impacts generation from natural gas, combined cycle units or gas turbine units in an evolving energy system. And you'll see more of that in an example that Emre will do. Vijay also mentioned that SESAME is been under development now for about 3 years. We have begun with a 3-phase approach to this. The first phase was conceiving and developing this modular structure, which is so key. And then to fill that out with an LCA analysis focused on North America, focused on the US system. In phase 2, which we are nearly done with, we are developing a parallel techno-economics piece that goes with this. At the end of the day, it's of course important to know the life cycle emissions and how that compares with from one pathway to another, one business opportunity to another, but knowing cost is going to be critical. And so we have that just about complete. And the third piece is starting to fill out the emerging technologies. What's in the model now is basically existing technologies, which will account for more than 50%, we think, of the emissions reductions going forward over the next 30 to 50 years. But we need emerging technologies and perhaps new technologies to capture all of that opportunity space. So that we've been developing with ExxonMobil. We've also begun a project with the IEA known as Energy Choices, which at its heart couples SESAME, which you're going to see here in detail, with a climate global economic model called EPA. That's the Emissions Prediction and Policy Analysis model. I think many members of OGCI are also quite familiar with that model. Now, Emre will actually give an example of a case study we've already done at MITEI in looking at those connections and how fruitful those can be. And that allows a smooth connection between the policy world and economics globally with a detailed model like SESAME. So a lot of advantages to the back and forth provided by coupling those two models. In the IEA program, we've also been adding in different, a variety of different environmental impact categories, land use, water use, and so on to couple an already broader set of greenhouse gas emissions we've put into SESAME. And then finally, with the IEA, we're developing a set of demonstrations of application of SESAME to other countries, regions around the world. We have one right now looking at a coupled Norwegian-German system, and one focused on Singapore as two very different kind of systems that we can illustrate the capabilities on and develop the database structures and database hooks into the system. So with that, I'd like most of this time to be spent with Emre so he can walk you through this eye chart and show you how you can actually assemble pathways and analyses that will inform uh, thinking, strategic planning, thinking, and decisions you make at OGCI and in your own companies. So Emre, I'm going to turn it over to you. Thank you very much.
Thank you very much, Bob. And thank you very much for everybody who is joining this call. We are really excited about this program. And so it's been 3 years I've been involved with this program. And I think finally we are getting some products out of it. So I hope you'll share the same excitement and we can work together. So I would like to start with a high-level slide, and then I'll do deep dive. And my presentation will be a hybrid. So I have some slides and also I will do a live demo. And fingers crossed about the live demo. You never know whether it works or not, but I checked this morning and everything was fine. So to start with, as Vijay and Bob mentioned in their remarks, basically we are seeing a huge convergence in the energy sector, and we now need to represent all sectors in a single tool if we are really want to understand the carbon footprints as well as the pathways to decarbonize the entire energy system. One of the challenges we see with this is the energy system is not static, so it is changing all the time, and we need to capture many parameters like technological options, operational, temporal, and geospatial variables. And when you look at the existing tools, I just want to compare with what is out there today and how SESAME differs from this. So as Vijay mentioned, so there are a lot of tools that are sector specific. So very detailed models in transportation, very detailed model in power sector, so on and so forth. And the second key challenges we are seeing is most of the models are taking into account some of these elements about technology, operational variation, temporal and geospatial variations. So with SESAME, we don't want to create a static tool. So it is pretty much dynamic. So you can use real data sets. You can run process simulations within the tool so that you can understand the operational variations, so on and so forth. But high level, the ultimate goal of this platform is really to assess and compare different technology options. And we truly believe that technology will play a huge role in achieving our decarbonization goals. We want to give a platform, a user-friendly, open access platform to perform technology and system scenario analysis. Also, we want to be able to explore implications of market and policy dynamics, which plays a huge role, and Bob mentioned about this, and our IEA program is really focusing on the policy aspects of the this approach. And cross-sector comparison is another key area that we are really enthusiastic about, and I will show one example connecting power sector with transportation sector and how important it is really to have a full representation of power sector if we want to really understand the carbon footprint of power transportation sector. And finally, the importance of standard versus best practices. So one of the key areas that OGC is interested in is, for example, energy efficiency. And the impact of energy efficiency can only be explored if we have a full representation of different options. And coming back to the eye chart that Bob introduced, and I really don't want to go into too much details of the eye chart because I will come back to this slide as the running team here. But I want to highlight one key focus here. So this is a systems level and pathway level technology assessment tools. Basically, you can build different pathways, and I will give you a couple of examples about pathways. But more importantly, you can define systems. And these systems can be as small as 2 pathways or as large as pathways that can define a region, a country, or a complete energy system. these systems can also be the portfolio of a company. So if you want to, for example, calculate your carbon footprint and do a decarbonization pathway for your company's portfolio, then we can also define a company's assets as the system of interest. And we really want to provide insights on the feasibility, scalability, and emission reductions of various technology pathways. So we are developing this at MIT. That's why we are really interested in the technology piece, engineering piece. And one of the features that we've built into the tool is on the processing side as well as on the end use side. In the process side, as I mentioned, we have developed process simulation capabilities. So basically, if you have a SPAN Plus or any other process simulations in hand, then you can connect that to our platform. And then you can see what it's doing in the full energy system in terms of emission reduction or how it's integrated to the rest of the energy system. And on the end use, we want to capture the systems dynamics. And for systems dynamics, you need a fleet model. And we've so far built two fleet models, one on power system, and the second one is on transportation, vehicle fleet model. And these models are connected to the rest of the tool. And I will give you examples of how we are using these capabilities and how it can be further expanded. So I want to start with one example from the power system. And here, as Bob mentioned, using these tools, we can build more than 1,000 energy pathways. And this is approximately 90% of energy-related emissions in the US. So basically, we can represent almost 90% of the emissions in the US by combining different pathways. And I want to give you an overview of one single pathway, and I will open the tool and also do this. Instead of showing you the results, I will do the demonstration live. And here, the way I will use this chart is the activated modules I am highlighting in blue, and the pathway I will first build will be shown with white text. So you will see here. So one key area that's been shared with you a couple of times this morning is the modularity. And how we define modularity is really the key of the engine of SESAME. For each one of these boxes, as we call it modules, there are connections to the previous step as well as the next step. So we have a huge connectivity matrix that defines all possible connections. And if the user is picking a connection that is possible, then you can build that pathway. But of course, what you are seeing here is a very brief subset of the existing sub-modules and all the tools that's within the tool. So basically, in the natural gas, I'm only listing here conventional shale gas, tight gas. But even in the natural gas, shale gas, or conventional gas, you can change the composition of these gases. You can look at the different locations where it's produced with different methane leakage rates, so on and so forth. Similarly, for each one of these operations, we have many more options that is built in the tool, or you can add as you go. So I want to just show how we built a pathway here, and then I will move to the tool. So here, when I pick natural gas conventional on the upstream, and in this case, I am starting from upstream and I will go to end use. So I have potential connections to many of the midstream operations like compression, separation, liquefaction, or transport or flaring. And here I am picking compression as my first step and then pipeline for transport. And then after transporting, as you can see here, I have many options as well. On the power generation side, I can use a steam turbine gas turbine combined cycle unit, or if I go to industrial processes, there are many processes like hydrogen production, DME production, methanol production, so on and so forth. So for this example, I'm going with a combined cycle unit. Then the electricity produced is transmitted and distributed, and the final goal here is to supply electricity. So let's call this P1, pathway 1, natural gas to electricity. When we look at the pathway, so it looks like we have defined everything, but actually we have not, because performance of power plants are sensitive to many externalities, including percent loading. And as we see increased renewable in the system with variable intermittent availability, what we are seeing is actually the balancing role is shifted to natural gas power plants. So combined cycle units were mostly baseload power plants, and now they're helping with the peaking power as well as balancing the renewable energy sources. So in the example that I will showing you, I would like to explore what is the impact of percent loading in the overall greenhouse gas emissions for combined cycle units. So I will switch to the tools now. And this is the user interface that we built in MATLAB. And also I think it's good to mention it right now. So this is the first version we built. And now we are moving everything to Python and a web-based version, so that you will not need to have a MATLAB license to use it. But for this demo, I am going with the current stable version, the MATLAB version. And here you can see we have a pathway analysis tab, system analysis tab. I will go into it. Results that captures all the runs that you have done, and sensitivity analysis if you want to do a sensitivity on any of the parameters that goes in. And I'll start with the pathway level analysis, and I would like to build the natural gas to electricity pathway that I've shown. So here you can see I can pick conventional gas or shale gas. There are transportation and processing options, and it can be pipeline, rail, ship, processing, compression, separation, and I'm going with the default mixes, and default mix is the default mix like of the US. For the processing, here I have a list of processes that takes natural gas as the feedstock, and we are building the power generation module. And here you can see we have options, combined cycle, gas turbine, subcritical and supercritical power plants. And for this particular example, I would go with the combined cycle unit. You can toggle on CCUS, and for this example, it will be off. And end use, I can either use as in a battery electric vehicle, or it can be electricity supplied to the grid. And also you can see we have many basic inputs here. So global warming potential, the functional unit of interest, the units that will be displayed, and for other cases that depends on grid electricity, emission intensity of the grid, and whether we want to perform a sensitivity analysis or not. And let's run this case. And here, this is the results showing for a combined cycle unit from GE, and this is a 7-frame GE unit. If we run it at full load, then the emission intensity is approximately 460 grams CO2 per kilowatt hour electricity. So what I want to show you here is when we change this loading to a lower level, let's say 80% of the nameplate capacity. As you can see, we are seeing an increase in the life cycle emissions. So when we move to 60%, it is further increasing. And when we go to 40% loading, part loads, we are seeing an increase in life cycle emissions, almost 20%. And the reason I went down to 40% is because currently most of the combined cycle units in renewable rich areas are ramping down to 40% level. So this is not an uncommon emission profile for combined cycle units. But more importantly, we can also do a comparison with gas turbine units. And here you can see we have quite a lot of different options for gas turbine units. Let's pick a 5-frame gas turbine unit from GE. And the reason I have these exact models is because in the backend, we have developed process simulations using Aspen to represent these power plants based on the GE's catalog information. And using that simulation, I can actually estimate the emission intensity under different loading conditions. So here, for a gas turbine unit, of course, as expected, the emission intensity is quite high. But what we observe is when we move to the 40%, like nameplate capacity, part loading, you can see the emission intensity increase almost 50%. So just to give you a comparison, so this is similar to a coal power plant emission intensity. So the reason I wanted to highlight this is if you don't have a process level understanding of these units, actually you really don't understand the impact of operating these under part loading conditions. And here you can see there is a drastic change, even in the combined cycle units, but also when you switch to gas turbine units under nameplate capacity versus part load capacity. And I want to go back to my slides and show you actually what does this mean in terms of the system. So in the California system, and we've used a big data set that I will also show you after this slide. What we've used SESAME for is we have collected unit level data for every fossil generator in the US for the last 17 years. And this is an hourly resolution data set, which is publicly available. And we have mapped different publicly available data sources to come up with a full representation of thermal power plants in the US. And what we have done in this analysis is from 2010 to 2017, we looked at the overall emissions in California as a response of solar penetration. So as you know, from 2010 to 17, the solar share increased from 1% to 20% levels. And the top row shows the combined cycle units emissions, CO2 emissions, and bottom row showing the gas turbine emissions. And here we have two colors, three colors. Gray is operation, red is shutdown, and blue is startup. So the first observation we have here is, even though we are seeing a huge increase in the solar generation, we are not seeing a huge decline in the overall emissions, although we are seeing a decline. And secondly, we are seeing an increased share of emissions in the startup shutdown period of combined cycle unit operations. And for gas turbine units, we are seeing an increase in the overall system. So there is a significant increase in the gas turbine related emissions. And when we look at the emission intensities, most of these emissions are coming from startup and shutdowns.
Emre, sorry to interrupt. Would you mind switching to full screen presentation view, please?
Sorry, I thought I'm doing full screen.
Thank you. Sorry to interrupt.
No. Thank you for telling me. Can you see the full screen now?
Yes, thank you.
Okay, perfect. And on the right-hand side, you can see basically the fraction of the emissions coming from startup and shutdowns versus the operation. And basically here, you can see for gas turbine units, most of the emissions are coming from startup and shutdowns. And for combined cycle units, we are still seeing a huge emission from operation. And these emissions are mostly due to part loading. And these part loadings are coming in the early morning hours, but also startup and shutdown operations are increasing. So how we've implemented this in the tool is actually going back to the tool. in the systems analysis, the first tab we have is the power grid. And for this power grid section, and I have pre-run this because it takes 5 to 10 minutes depending on the day I run the model. So basically here you can see for California, Texas and PJM system, we have all the units based on their categories, combined cycle, gas turbine and steam turbine units. And within each power plant, so let's pick a power plant here, which is El Segundo, and we have 2 units here under this. You can see the load profile of these units. So what I want to highlight here is when you look at these load profiles, and now I am focusing only to 1 month of operation, we are seeing a huge gap in many of these places, right? So we have a startup running a couple of hours and a shutdown, and similarly another startup and shutdown. And here in this case, we are seeing a significant cycling over the couple of days or couple of weeks. And let's pick another example and let's look at the full year here. And also we can look at the percent loading of this unit. So here you can see for many of the hours it's been operated, it is cycling down and up, and we are seeing a frequent startup and shutdown for these kind of units throughout the operating regime. And also we can look at the load duration curve, and you can see how it is operated at different loadings all the time. And basically using all of these data sets embedded in SESAME, we were able to really go back and understand what fraction of the operation is causing more emissions, and how we are seeing an unintended consequence of penetrating more solar energy without necessarily understanding how it will be balanced in the system. So coming back to the presentation, what I want to show you is another example from the transportation sector this time. So for the transportation sector, I would like to focus on first internal combustion engine vehicle. And here I will pick a conventional oil, which was transported through pipelines, refined in a refinery and transported in pipelines, and final product will be gasoline, and it will be combusted in an internal combustion engine vehicle. And here the way we will do it is when you look at the tool, I'm going back to the pathway analysis, and now I will switch my focus to crude oil. And here I have different options for crude oil, but basically in the Python version, we have hundreds of different options, not only 3. I'm going with the transportation. I picked my product gasoline, and here I have 11 different refinery configuration. And you can pick different configurations here, and based on the configuration you are picking, you will see a different life cycle emissions for the same product, same gasoline. And I'm picking a medium conversion FCC post, and the product will be light duty vehicles for this example, because I want to see the internal combustion engine vehicles emissions. So here we've easily calculated the internal combustion engine and LCA based on gram CO2 per mile driven. But this is the entire chart that we are seeing here is only looking at the fuel production and fuel consumption. Basically, this is operational emissions. And now the discussion is about the comparison between electric vehicles and internal combustion vehicles and hybrids. So actually a relevant question is how much of a difference we see not only in the operational emissions, but also in the car manufacturing. So when we go to the systems analysis piece and one car emissions, now actually we can do all of this analysis here. So I will start with the gasoline internal combustion engine vehicles. And here I have my assumptions. So basically you can pick the model year, and we have a fuel economy assumption for different years. You can pick the VMT, battery replacement, and grid decarbonization rates, and where it is located, and also the fraction of in-city operation versus road transport. And also we can pick the MPG based on different vehicles. But here I am just going with a representative vehicle and running the analysis. And here basically what I will see is not only car operation, but also car manufacturing, car production analysis piece. And I want to add a hybrid vehicle to compare with here. And when we add a hybrid, the emissions are, operation emissions are going down as well as total emissions, but you can see a slight increase in the car production emissions. And now I can switch to EV, and I'm not playing around with the assumptions because I will show you more detailed analysis on the slide deck, but just to demonstrate, when we move to EVs, actually you can see, and this is for the grids for Kansas City, the overall emissions are going down, but the car production emissions are increasing. And here we can change the battery replacement assumption to none to once versus twice, as 180,000 miles is a little bit high for one single battery set. Actually, you can see how much of a difference car production makes here. So in the operating emissions, you can see what fraction is coming from tailpipe versus fuel production. And of course, here we don't have tailpipe emissions for the electric vehicles. And on the car manufacturing, you can see basically what is causing the car manufacturing emissions. And here I am showing you the battery electric vehicles. So basically here you can see blue is the batteries, because this is the latest example I use. So it is significant when you have twice replacement of batteries. Also, you can do comparison of two car production emissions in the tool to really understand what is the impact. And I want to also show the last piece in the SESAME tool, not to go back and forth, and I will switch to a presentation after this. So as I mentioned, we have also developed a fleet model within the SESAME tool. And this fleet model takes various assumptions about the adoption of different technologies and their emission intensity, fuel economies, so on and so forth. And here we have two options. Either we can use one of the existing projections. It can be from EIA, IEA, or from EPA model, joint programs assumptions. And we can populate this table with those and run the model. And when we run the model, we'll see how the stock is changing and what is the energy use by fuel type over the next 20, 30 years. We can also calculate the greenhouse gas emissions, life cycle greenhouse gas emissions for each one of these years. And we can play around with all the assumptions. And another approach we can take is actually we can here enter all of these assumptions as a user, and we can define our own projections and see what our scenario will look like in the fleet level, like system level totals. So I will show you two examples from these in the slide deck, and also I will show the connection between electric power system and the transportation. So let me switch to the slide deck. So as Bob mentioned, we have already used this tool in many studies, including the Future of Mobility study that we've published. And here for the life cycle emission piece, we've used SESAME, and here you can see the comparison of different powertrains, internal combustion engine, hybrids, plug-in hybrids, battery electric vehicles, and fuel cell electric vehicles, and how they are ranking compared to each other. And here the one shocking result was that actually hybrids, plug-in hybrids, and fuel cell electric vehicles using steam methane reforming without carbon capture are quite similar. And we see for US average grid decrease over other options for the battery electric vehicles. And also we can observe that the vehicle production piece becomes more important when we have larger batteries in the vehicle. But there are really two pieces that SESAME tool can really add value. And I will show you one on battery electric vehicles versus hybrids comparison, and the second one is on the fuel cell electric vehicles and hydrogen supply. So the first one I want to show is on the hydrogen supply. To really understand the hydrogen fuel cell electric vehicles carbon footprint, we really need to understand the hydrogen production. And here we are very well prepared to compare various options of hydrogen production methods as well as full supply chain using different modules. And here just I am showing which modules will be activated to do this analysis. And the results are shown here. And for these results, the projection piece is informed by EPA model. So this was our first collaboration with joint program for the emission intensity of the grid, as well as improvement in vehicle performance. We read these data sets from EPA model, and the rest life cycle emission is done using SESAME. And here the basic comparison is different hydrogen production methods, all shown in blue. Solid is electrolysis using grid, dashed is SMR, dotted SMR with CCS, and the last line is fuel cell electrolysis with wind power. And the colors are black is internal combustion engine, red is hybrids, and green is battery electric vehicles. So here the first observation is basically how we produce hydrogen plays a huge role in the relative ranking of fuel cell electric vehicles. And it can be anywhere from the highest emitting powertrain to lowest emitting powertrain. And also another interesting observation here is even if we don't use carbon capture, a natural gas-based hydrogen production using SMR is quite on par with hybrid electric vehicles. So this is also an interesting result. And finally, I want to highlight this bottom curve, which is electrolysis only using wind, and the emissions even in 2050 doesn't go to zero. And the reason for this is we still have the manufacturing piece. So we are manufacturing the vehicle, building the wind turbines, so on and so forth. And for all of these, there is a life cycle greenhouse gas emission. And unless we completely decarbonize the system, including manufacturing, we will always have some residual carbon emissions, greenhouse gas emissions that will eat up from our carbon budgets. And quantifying this is really important to really do realistic estimates and projections. And the second piece I want to briefly mention, I know I'm on my time limit, so the relative comparison of batteries and hybrid electric vehicles and how these results are changing based on the location and based on grid emission intensity. So if we are in a state like Washington where there's quite a lot of hydro in the power mix, then battery electric vehicles are very advantageous. But if we are in Indiana, where in the power mix there is still coal, then hybrid electric vehicles are more greenhouse, can further reduce greenhouse gas emissions relative to battery electric vehicles. And here, adopting hybrids can be more advantageous. And this results change throughout the country. But furthermore, this also, the battery electric vehicles and their emission intensity is also affected by how we charge it, when we charge it. And here I wanted to show you the connection between our power module and transportation module. Basically, we have all these profiles about generation by source, percent generation, and life cycle emission intensity at different hours of the day, different seasons, different days of the year, so on and so forth. And basically, this just shows you that if you're in California and if you are doing midday charging, your emission intensity is quite low. But if you are in New York, actually your overnight charging is less carbon intensive than your midday or evening charging. And even these are changing based on the locations and based on the rest of the system. And unless you have a tool like SESAME, it's really hard to quantify all of these options. So I had another example, but I think we will share the slides, so I will not go into the detail. But here we've looked at an option where we are increasing the renewable penetration for a system, and we are seeing a change in the percent generation throughout the day from different sources, and how it is impacting the emission intensity of battery electric vehicles and their depending on their charging times. And so you can see this is not an insignificant impact. So, and this needs to be definitely part of the policy discussion when we are talking about EV adoption policies or incentives, and as well as it has huge implications for the power system and the flexibility of power system. And all of this basically can be, at least the initial insights can be gained using SESAME. So one final example about the fleet model is basically, I here compared two projections for vehicle fleet adoption, EV penetration. One is EIA's base case scenario, the other one is from Bloomberg Energy's very high level EV penetration scenario. And I want to highlight this bottom chart here. So we have calculated the life cycle greenhouse gas emissions for both these two cases, and you can see the EV share is quite different in these two cases. And this is using our fleet model that I've just shown in the tool. At the end of the day, in 2050, either we have a very high EV penetration or not. Actually, we are seeing a similar greenhouse gas emission level from transportation, light duty vehicle transportation. EVs are a little bit lower, but not quite. And the reason here is still the same. So we still need to manufacture vehicles. We need to manufacture wind turbine, solar PV panels that will generate this electricity. And also we will see a fuel economy improvement in internal combustion engine vehicles, which is also reducing the greenhouse gas emissions of transportation fleet, although we are seeing an increase in the total fleet number. So with that, I want to highlight one more time that SESAME is a very modular tool, and we built in a very flexible manner just to be able to connect with different tools. It can be company-specific tools, proprietary data sets, other data sets, or other tools like EPA model, integrated assessment models, capacity expansion models. We just need to define input-output relations, and then you can basically connect your tool to the SESAME platform. And here's a list of current projects and publications that we've already published, including one working paper from our IEA project, Mobility of the Future study, two examples from solar PV and wind power, and also one paper that's discussing the methodology and giving some of the examples that I've shared with you. And on the right-hand side, so I have a list of case studies we've used SESAME for, and all of these are actually currently drafts that's under review in different journals, and hopefully they will be coming out in the next couple of months. With that, I would like to thank the team before finishing up, and I will stop in the key takeaway slide. So we have a really big team working on SESAME development. So we already have some alumni who contributed significantly to the SESAME project. But as you can see, so this is not a small group. So we are, and as Vijay mentioned, so this is a evergreen project, and there are many questions to be answered, many modules to be developed, and this is basically all the contributors to the SESAME project. And I would like to stop here and thank everybody for your attentions, and we are happy to answer any questions. So I will leave this slide if it is okay. So the key takeaways about on our slide deck.